previous talk was about the present. Now we are living present and we take a journey to the future. So, so probably all of you have heard about Schrodinger's cat. So what is that cat? Well, you have just a normal cat, but there is a radioactive material in front of the cat. Now you know that radioactivity is a quantum process. So if you view the whole system as a quantum system, then what happens is that, well, depending on whether this radioactive heap decays or not, the cat dies or stays alive. So apparently, according to quantum theory, what really happens is that both events happen at the same time. So what really happens is that the cat both stays alive and just So now, actually I'm set to tell you the whole thing. So can this cat break codes? That's the topic of this talk. So I have to introduce you two topics, right? About cats and codes. So I start with codes. So what is a crypto system? Well, a crypto system is just that you are the government, let's say, and you have a spy somewhere, and your spy wants to send a message to you. So what happens? Like the spy has a secret code, and you have a secret code, and so we are talking now about private key crypto systems. So what happens is that when the spy, let's say the spy is on Seychelles Islands, and so it just adds this secret key to this binary string, which is his message that he wants to send to the government, and meaning bitwise, and so there's a number, and there is the eavesdropper, so the opponent's spy. But since this message, this 1101 is scrambled by the secret key, the eavesdropper does not learn anything, and when the government applies the same secret key, namely adds it binary to the message, then it gets back the original message. So for this scheme, both the spy and the government has to have the same copy of secret key. And if they lose the secret key, then that's it. Then the eavesdropper can learn the message. Now this crypto system is not viewed as a good crypto system because you can use that key only once. So this is not the crypto system that you want to use. So how about making the key public so that when we lose it, then we don't lose anything? Well, we can make it public, of course, but then the problem is that then it's not secret anymore, right? So how about this? That we have two keys. That we have a public key and a private key. So with the public key, anyone can encode a message, but to decode a message, you need the private key. So actually this is the idea that so we are making decoding easy if we have that secret key that only the decoder has, only the government has. So the spy has the public key. So the spy can lose the key, the eavesdropper gets the key, still the eavesdropper can't decode the message because it does not have the other key. Now, so how is it? Actually, this idea was the idea of Rivest, Shamir, and Ademan, and this is the famous RSA crypto system. And this is called public key crypto system. So the public key crypto system really works like that. So you imagine you have this, you know, these locks where you have this door knob where you can actually, even a stupid person can lock the door, and actually only a stupid person locks the door without having the key. But you lock that your secret into behind the door, you lock it, like everyone can do that, but then you need the key to open it. So the locking procedure is much easier than the opening procedure, because for the opening procedure you need the key. Now let me give you an example how you can implement this in mathematics. So this is how RSA works. So let's say you have your score on exam is 67 out of 100. Now you might not be very proud of that, so you want to send it through a channel that no one learns your score. So what happens is that you are taking the 27th power of the score, and well, that's 23 modulo 100, and that's what you send over to your friend. So you send over 23. Now how does your friend decode it? Well, your friend just takes the third power of 23 and miraculously gets back 67. Now why is that so? Well, because there is a number theoretic statement that if you take a 27th power of any number modulo 100, which is relatively prime to 100, so you can't do it with 65, but you can do it with 67, and then you take the third power of that, then you just get back the original number. So in general, this RSA scheme works like that. That here is the message, you take some appropriate power of that message modulo n, and there is kind of a complementary power, like if for k, so that was 27, the complementary power was c. So if now you take, you are the receiver, you are the receiver, you receive the message, I realize that's not, then you receive the message, then you are taking the complementary power and you get back the original message. Now I've told you RSA. Now you see that so now you are asking, so why is it good? Why is it a good crypto system? Now well, with 100 it's not good, because every number series knows that if you take the 27th power and then you take the third power, then you just get back the original number. But if you create now, so let m be a random number which is a product of two primes, then you can create a system with two complementary numbers, k and s, such that this system works like before, as I explained. But now, so the code breaker could still try to find the complementary power x. So what does it take for the decoder to find that complementary power? Well, it turns out, and I just can't get into the details, that it's enough to find a power such that for every number, that power, if you take that number to that particular power, then it is going to be equal to 1 modulo n. So that's enough. Just so this n is the modulo, which is like a random number, and so if for that particular n you find a number t such that if every number you raise any number to that t, you get 1 modulo n, then you can break the previous crypto system. So in particular, it turns out that it's enough just to find for a fixed random number something like this t, such that for that fixed random number, the t's power is 1 modulo n. Now, if you think, okay, so you are saying it's easy. Well, it's not so easy, right? If I have a 200-digit number and I have another 200-digit number, now I'm asking like a 200-digit random number. So what is the power that I have to take that other 200-digit random number such that it's going to be congruent to 1 modulo the first 200-digit number? So how can we find such a number? Well, it turns out that what we can do is take our random number and just take the subsequent powers, like the first power, second power, and so forth. And if we do that, so let's look at an example. So let our modulus be n, 10, and our random number be 3, and then just start to take the powers of 3, so modulo 10. So 3, 9, 7, and then 7 times 7, 7 times 3 is 21, right? So the modulo 10 is 1, and so forth. So you see that it starts to repeat itself. So actually the period, which is 4 here, is the repetition period, is that power you are looking for. So that's 4 is what we are looking for in this case. Now in practice, however, if n is not 10, but it's a 200-digit number, then the sequence is terribly long, like it's 10 to the 200, and no one can write down such a long sequence. Now here we look back to Schrodinger's cat, but before that I am now stating the abstracted problem, which is that, so given a long periodic sequence, we want to find the period. And somehow the periodic sequence is not gonna be written down like on a paper. But what is going to happen is this. So let's now go back to this cat. And just so notorious, I won't be able to erase it. Or is there any way to get rid of those copies of the cat? Thank you. Actually, I'm Okay, so get back to quantum mechanics. So 10 minutes. Okay, so assume now that we have actually two cats, a black cat and a white cat. Right, so here you have the gosh, so I mean, it looks like a pig, but here we have the radioactive thing. So now, of course, according to quantum mechanics, now this will get into 4 different states simultaneously at the same time. So there's the miracle of the nature that here you have, well, now you have to write a white cat alive, right, and a black cat alive, and then a white cat entirely dead, and a black cat entirely dead, right? So it's kind of complicated, but not as complicated as Schrodinger's equation. So now, actually, theoretical computer scientists have too much time, so they started to think about, instead of cats, they started to think about bits. So the bits, so now the cats are bits, like it's either dead or alive. And actually you can have more than 2 bits, you can have n bits. So, but when you do the bits, so actually they like to note it like this. So it's like, let's say alive is 1, so you have these n bits. And so there is some random process, and then they stipulate that you can put these bits into like all 2 to the n possible combinations. So you can put this state, so as they call it computer, you can put this state into a quantum state, which is a superposition of all these 2 to the n combinations at the same time. So now this point, maybe let's be more precise. So what does it mean that all these states coexist? So that saying that is not as mathematical as we would like. So this is what is actually being said. So now using the terminology what quantum people use, that this state is 1 over square root of 2 to the n times this plus, so this is a mathematical formalism which the square root of 2 to the n, so this is the mathematical formalism which expresses the state of our system. And it says that our system is, if we do a measurement on our system, then this 111 turns up with cross. So then we do a measurement that we only say one event, either 111 or 000 or some combinations of zeros and ones, and the associated probability is going to be the coefficient associated with this event. The square of the absolute value square of the coefficient associated with that event. So that is called an entangled quantum state. So you see that whether it's dead or alive, so there is a measure to that how much is dead and how much is dead and how much is alive, right? So but now that's not the whole story. There is an interesting angle to this story, and this is this, which I should actually underline or write with big red letters, which is that interference. And maybe I should really write it with red. Now what is that? So that comes into play when we have a process, when we have a quantum process. So, so now let's assume that our system is in the state 1 over square root of 2, 0 plus 1 over square root of 2, 1. So this means you measure it with probability measure it, and with probability half you are dead, with probability half you are alive. Now, what does that state mean? I'm sorry. Minus 1 over square root of 2, 1. Now this is another entangled state, and if you measure this entangled state, then what you see is also that your cat is with probability half is dead and probability half is alive. Now does it mean that these two states are exactly the same? Well, it does not mean that. And here is why it isn't. Because assume now that there is an outside effect comes. And the outside effect in quantum mechanics comes as an operator. So your operator is this, 1 over square root of 2, 1, 1, 1, minus 1. So what does that mean? Well, let's see how this operator acts on this state and on this state. So, so let me call this H. And so what it means is, what this operator means is that if you have so 1 over square root of 2, 1, 1, 1, minus 1, now this state is written as a vector 1 over square root of 2, 1 over square root of 2, and the column vector 1 over square root of 2, 1 over square root of 2. So this is going to be then 1 over, yeah, this is just going to be 1, 0, right? So what does it mean? That if we apply this operator on this state, then we get that the cat is just going to be alive with probability 1 and dead with probability 0. Actually it's the opposite, because the first coordinate means the 0 and this means the 1. So it's dead with probability 1 and alive with probability 0. However, if we apply the same operator on this state, then, well, you can compute that it's exactly the opposite. Then you get 0, 1, which means that the cat is alive with probability 1. Now the key to this miracle is that, well, there is an interference, different things cancel out. So in quantum mechanics, unlike in statistics, since we are dealing with both positive and negative numbers, then certain things cancel out. Now here we are looking back, finally, to how this cat can factor numbers. So here is how it's going to do it. And it's really just a very, very superficial way of explaining it. So here is your quantum computer. So originally, your quantum computer is in the state, let's say 1, 1, 1. So all the cats are alive. Now, this quantum computer sends them out in the superposition state, which is just the all combinations of dead and alive. So 1, 1, 1, 0, 0, 0. Actually with equal probability, so each with probability square root of 2 to the n and square root of 2 to the n. And I shouldn't say probability, I should say amplitude. So in quantum mechanics this is called amplitude. So now, however, actually this quantum computer has another register, and this other register is not used yet. Now, I know that in 15 minutes it's hard to explain what quantum registers are, I mean in 2 minutes, but so what it does is that like in each branch of the world, so you can think of these as different branches of the world. So in each branch of the world, this quantum, so you can think of this that these are different quantum different computers starting from different inputs. So in this branch of the world, it just so this I call X, and so what it does, it now just takes X and it computes X. I'm sorry, I should, yeah, just, I apologize, I should call this Y. So and then it takes X to the Y. So actually it takes, so this is, and I should say, so this takes, so what it does is, like it puts it into the superposition of this, like sum 1 over square root of 2 to the n, and here you have I, and here you have X to the I. Now, if you recall from here, now you have this periodic sequence, right? So what you see here in the second register, like in this sum, you see that this second register is like periodic. as I goes from 1 to 2 to the n, you think of these as binary numbers, and actually you should think of this as coming this way, so these are binary numbers, then so you get, so these are the contents of the second register. And this is the state of your quantum machine. And now what Peter Shor observed, and that's his great observation, that once you can put your quantum machine into this state, then this is what happens. That now you apply a Fourier transform, which is just a matrix that I drew, except that in 2 to the n dimensions, so you apply a 2 to the n dimensional Fourier transform on the first register, which is a quantum transition, and what happens then is that now if you measure the second register, that because of the periodicity of this sequence, so because this sequence is periodic, you will, if you measure the second register, you will see like this, you will see peaks exactly at those points. So these are the multiples of period. So this period is 4 here. So these are going to be the multiples of that period that you are looking for. So what happens is that now if you do it a couple of times, you just get a lot of multiples of that period, and for that, the period that you are looking for, you can actually compute. So now I left a lot of questions, of course, open. So this is like introduction into two things, codes and quantum computing, and Fourier transform, and how you do Fourier transform on the first register, and so forth. But if you can do that, then you can just break codes, and then you can go to Scheissel Islands and just beat all the spies. Right now, so let me just spend one sentence on the reality of this whole thing. So actually in Japan, they are trying to build, and they are building quantum computer. Now they told me that there are several technical obstacles, but they are still building that. And so one thing, that there is this physical thing, which is what is called ion trap machine. And actually you can, if you go to the web, you can see these nice pictures of the ion trap machine. So they even have a picture how it's gonna look like. Now, I think when it's built, it's a couple of decades away, but if it's really built, then what you can do is you can always find periods in sequences, and what is now the hottest research topic in quantum computing, in the theory of quantum computing, is whether you can do other things than finding periods. So far, this is the only thing what you can do with quantum computer, finding periods. Actually, if there is just all zeros and there is 1, let's say, then you can find that 1 a little bit quicker than with classical computer. But if it's periodic, and it can be an exponentially long, so that the key is that it's not just, it's an exponentially long period, so there is no way to write down that sequence and find the period classically. You can do it quantumly. So that's, really in a nutshell, that's what the state of art right now about quantum computing.
Classically, what would be the complexity of this problem if you wanted to solve it classically?
Well, exponential. Exponential because the sequence is exponentially long, so you would need to store, like if it's 200 digits, then it's like the sequence is of length n to the 200. If it's 1,000 digits, the sequence is n to the 1,000. You can't even write down a sequence of length n to the 1,000. With quantum computer, you can do this because this 2 to the 1,000 things live at the same time, so they are just there. They are just simply there. And maybe I should tell you that you believe it's science fiction, but so recently I visited Eddie Farkey, a MIT professor in physics, and he said that some people tell me that that they never met quantum phenomenon, and to that I can just say that, well, I never met any phenomenon which is not quantum phenomenon. So, I mean, we were at dinner and he showed that like the way how the light shines from his fork is actually a quantum phenomenon, and everything is quantum phenomenon. So, it's there, it's lurking, and it's waiting to be discovered. Yeah?
Why is square root used in the formula?
Oh, because in quantum theory, these amplitudes, you always have to square them in order to get the probabilities. So that's, actually these operators are not stochastic operators, but unitary operators. They keep the L2 norm. And so this is actually the L2 norm of this expression is, this vector is 1. I mean, it's the square of the L2 norm. Yeah.
We have to
wrap
it up, unfortunately. Now you see why we hired Mario. He is really smart, right?